Okay, so I believe it's the today afternoon is the festive party at MPIA. So we'll start a little bit earlier, maybe before the bus comes. It's my pleasure today to welcome somebody you will all know pretty well, to some extent at least, Philipp Girichidis, who's working at the ITER, and he has just been recently appointed as private docent there by Heidelberg University. And he's going to be talking about, as you can see, cosmic rays in his telemedium. But the journey started, I think, also in Heidelberg when you did your PhD, 2012. And as far as I can understand, this was quite an interesting PhD because you spent it in at least 3 places, right? That you were, I think you started off in Heidelberg, and then one of your supervisors, who was Roby, left at some point to go to take a professorship in Hamburg, and Ralph was the other supervisor here. But you also had funding to go to Cardiff, I guess, Cardiff University. See if you can get it to come back with any luck. I'll continue. Yeah. Oh. Anyway, Cardiff University. And then that work was on a relatively small scale compared to the topic of today, which was the importance of initial conditions for star formation. So it's about structure and collapse of molecular clouds to form stars. Thereafter, you went to Garching for 4 years after a postdoc, which I think was in the context of this simulating the life cycle of molecular clouds. And if I get this right, that you were then expanding the scope of these calculations onto galactic scales involving large-scale feedback processes. And then in 2016, you returned for a year here, where Christoph Frommer was working at the HITS Institute at that time. And that's, I believe, when really you got into the cosmic rays in a big way. You produced new software which allowed efficiently the calculation of the transport of cosmic rays in position and energy in these hydrodynamical simulations on galactic scales, I think, for the first time. And I know that there were a number of influential papers that came from that time. And thereafter, when you followed Christoph to AIP in Potsdam, and then after 4 years in Potsdam, good news for us, you came back for a third time in order to sort of continue this big project where I think you have been in expanding the physical scope of these simulations and into using the increased computing power available. And I think that's what you are going to be telling us a little bit about today. I'm intrigued to see what the status is in terms of cosmic rays and galaxy evolution. So please, Philip, take it away. Thank you.
Thank you very much, Richard, for the introduction. Yeah, I like Heidelberg very much, and that's why I'm also very happy to be invited here to give a talk on my work related to cosmic rays and in the interstellar medium and their dynamical impact. So let me start by mentioning a few historical facts. So cosmic ray physics is something like a bit more than 100 years old. The first person to deal with these rays was Theodor Wolff. He invented the electrometer and then made measurements of the radiation on the Eiffel Tower, on top of the Eiffel Tower and on ground. And he found there's increasing radiation on the top. Then 2 years later, Domenico Pacini made experiments below the sea level with basically the same result, measuring the radiation at the sea level and far below, and he found that the radiation was higher at sea level compared to further down. Then this main event that basically now in the history books is referred to as the starting point of cosmic ray physics is the balloon experiment by Victor Hess in 1912. And he again found the same thing. Up in the balloon, the radiation was stronger compared to on Earth. So people were pretty certain about what they did. And interestingly, only a few years later, Millikan wrote that we already have some solid knowledge about cosmic rays. He wrote, we can draw some fairly reliable conclusions of a general sort as to the origin of these very penetrating and high frequency rays. And that's all wrong, because we know now cosmic rays are not rays, they're particles, and they have completely different properties compared to the high frequency rays that people thought back then. So we know there are protons, electrons, positrons, and heavier elements. I will come to that in a bit. Let's first look at a measurement of cosmic rays. Here's the cosmic ray spectrum as a function of energy, and here is the flux. And there are two important things that you can directly see. First of all, it's a huge dynamic range in energy. So here we have a GeV, here we have 10 to the 18. So overall, we have like 12 orders of magnitude in particle energy. And the dynamic range is also huge. So here you see 8 orders of magnitude, but that spectrum is already multiplied with E squared. So they're probably like 20-something orders of magnitude in dynamical range. So that means here you have very, very high energies per particle, but only a handful of particles. If we look at the highest energy cosmic rays, we make measurements of a few particles per square kilometer per year or so. So hard to do statistics, but actually you can give them names, every individual cosmic ray. If we look at where most of the energy sits, then we see that the peak of the spectrum is approximately at 1 GeV. And 1 GeV is also the proton rest energy. So if we speak of protons, which is the red curve here, then this is the non-relativistic part, and this is all the relativistic part really to the ultra-relativistic regime. So before we go into details, it's instructive to cut this spectrum into 3 different parts. So ones are the low energy cosmic rays, basically the red part here in that arrow. And those cosmic rays can deeply penetrate into molecular clouds. And because of their lower energy, they have an increased cross-section with the thermal gas. So that means they can ionize the gas and can regulate the temperature in dense gas where normal radiation cannot penetrate. So for star formation, the heating of dense molecular gas, the chemistry in star forming region, those are the important ones. Then we have the GeV cosmic rays. Here is where most of the energy sits. So those are the ones that are dynamically relevant via an overall cosmic ray pressure. And if we look at the energy distributions in the interstellar medium, then the cosmic ray energy is actually comparable to all the other components. That means they are decent energy reservoir in the ISM, which can couple to the dynamics of gas flows and outflows and so on. And then we have the high energy cosmic rays. They are interesting from a particle physics perspective, but overall a very low integrated energy. So for the dynamics, we don't really care, but they are very important as observational diagnostics via gamma rays and so on. And I will show some of that later. There's one thing that is a bit tricky, and these are the very low energy cosmic rays in our vicinity. So here is a cartoon of where we live. That's the sun, that's the earth, and we are within the bubble of the solar wind and within the region of the heliopause, which means we are impacted a lot by the sun's feedback in terms of solar wind, magnetic field, low energy cosmic rays, and so on. That means at the low energy part of the spectrum, we have hardly any measurements. So fortunately, the Voyager spacecraft from 1977 or so still work today, and they made it by now out of the heliopause and can give us actually cosmic ray and magnetic field measurements of the interstellar medium. But that's just one tiny step out of our influenced surroundings. So we still heavily rely on some models how the low energy cosmic ray look like. I already showed you in the spectrum that we have different kinds of cosmic rays. I would like to make the distinction into primaries and secondaries. So for the primaries, we talk about the particles that are produced during the lifetime of a massive star and are then ejected and accelerated in the explosion that massive stars do, so in the supernova remnants. And those are important or fundamental to our understanding of the origin and the acceleration process. Contrary to these primary elements, we have secondaries, and those are primarily elements like lithium, beryllium, boron, fluorine, and they're produced not in the stars, but mainly via the interaction with the interstellar medium. So the primary particles shoot through the interstellar medium, they interact with the gas there and produce those secondary particles. And the important thing that we get from here is the properties of how cosmic rays travel through the medium. And if we have unstable secondaries, we also get some clocks from the production sites to the decay and what that tells us about the transport. This is quite a complicated business, but I would like to highlight this in one example. So a classical thing to look at is the ratio of boron to carbon as a function of energy, or here rigidity, and rigidity is simply the energy per charge. So if we assume that the cosmic rays are universally accelerated, and I will come to that in a minute, then we expect a similar composition that we have in the stars and in the ISM. So if you produce all cosmic rays with the same amount, then we would expect that we have very abundant alpha elements because they are produced in massive stars. We can now observe the relative abundance of these light elements, for instance, boron. And here, what you see, if we look at the ratio here, that it changes with the function of energy. So what we see that the boron to carbon ratio is larger for lower energies and is lower for higher energies. And what we can deduce from that is that if boron needs to be produced via the transport and the interaction with the ISM, then that means that low energy cosmic rays have a longer residence time in the ISM, therefore have a larger effective cross-section with the ISM and produce more secondaries. If you go to higher energies, you escape faster, therefore you have less time of interaction with the ISM and your unstable isotopes drop. So from that plot, we can already see that the cosmic rays with a higher energy escape faster. That's an important fact, and it depends on a lot of assumptions, but we will see later that this also fits nicely with spectrally resolved cosmic ray simulations and the resulting observables. Okay, so this is as much as I would like to mention about the general facts about cosmic rays. So why do we care in galaxy formation about those particles? And there are various anchors where you can connect cosmic ray physics to observables, but one fundamental problem that people had in galaxy formation for a very long time are outflows. So here you see a starburst galaxy, M82, in a Hubble image. You see the star-forming galactic disk, and you see here in red outflows. So this is the disk, probably a few kiloparsec, 10 kiloparsec, and what you clearly see are strong outflows far above the disk. Now, what kind of feedback processes are there? And if you take the classical feedback processes, what comes from stars, we notice that this feedback is just not powerful enough. We see outflow in all phases, which means even molecular gas needs to be transported somehow out there. But if we look at the classical feedback, supernovae cool too fast. That's a thermal explosion. The massive stars only live for a short amount of time. They all explode here in that orange box, and then the thermal energy cools very fast. Radiation can go very far, but doesn't couple efficiently. And then we have other things like stellar winds, protostellar outflows, and so on. That's just way too weak. Cosmic rays, however, are pretty fast because they're relativistic particles, and they cool very inefficiently. That's something we will talk also in a bit. So their energy can reach very large heights easily, and therefore do or deposit energy at very large heights. So that's one motivation for why we look at cosmic rays in galaxy formation. Let me start by looking a bit to the fundamental process where cosmic rays come from, and therefore how we connect them to the observations. So this goes all back to Fermi in 1949. And here the idea that you have clouds in the interstellar medium that move because of turbulent motions relative to another, and you have stochastic scattering processes of particles between those clouds. So you have something like magnetic mirrors, and then you have thermal particles, and they scatter off the one and the other molecular cloud, and therefore gain energy in every collision. So you have head-on collisions and following collisions, and what you can do is you can derive a change in energy that you get from these collisions. So change in energy is the energy that you get after two scattering processes minus the initial energy. And if you formulate that by transforming into the rest frame of the one cloud and the other cloud, then you get this term here, which a term here that depends on both velocities and some angle, and then a term that scales here with v over c squared. So you can do the averaging process and say, what is the average delta E over E that I get? So then this cosine term vanishes, and what you end up with is a term that scales with v over c squared. So that's a second order process. That's also called second order Fermi acceleration. And it looks good in a sense that you can get an exponential increase over time. However, the velocities are pretty small. So the velocity that goes in here is the relative velocity between the clouds. That's 10 kilometers per second. 10 kilometers per second over c is nothing. Squared is even less, right? Another problem is that the clouds are typically far away. So you have several parsecs between the clouds, which means that across these long distances, the losses are too strong. So the particles travel very far before they get another little kick, which means they lose more energy that they gain. Therefore, Fermi 2 is a very inefficient and unlikely the process that we're looking for. Then in the 70s, people came up with another idea. So there were several papers that dealt exactly with that. And the points are shocks. So what is a shock? If you move through a medium faster than the sound speed, then the sound speed cannot keep up with your speed. And therefore, you get jumps in the distribution of the density, the velocity, and the pressure. So this is a classical shock tube numerical simulation, and you can also put analytical parts to it. So here you see the shock front, here you see the density jump, and this is the interesting part for this model of diffusive shock acceleration. So what happens here is similar in principle compared to what you have in these cloud collisions. So you have, there's a nice cartoon here. You have the shock front, and then you have particles that go upstream and downstream, and every time they change the reference frame, they get another kick in energy. So if you do the math precisely, it's not too much, but too much to show here, then what you get out is that delta E over E is scales with the velocity over c. So that's a first order process. That helps a lot. The second thing that helps a lot is that this shock front is basically a well-confined structure. It's not random clouds at some large distance. It's one self-confined, well-confined structure. That means the losses while jumping or diffusing across the shock fronts are relatively little. So this is a very promising process, and it's awesome work from the 70s. However, there's also a few additional considerations that we would like to include and actually test this simplified theory. So here I would like to show how you attack that problem with simulations. So mainly of this diffusive shock acceleration is pen and paper work, which assumes an infinitely sharp shock. But there are a few additional considerations that you have to do. So there's a back reaction onto the fluid. The fluid will not be static. Then a real shock is not infinitely sharp. You have the transition of microscopic particles going from one regime into the other. And typically you also have magnetic fields, with it is a vector field, and therefore adds another complication. So what people do in order to attack that problem is so-called particle-in-cell simulations. And there are two main flavors of that, which are illustrated here. What they have in common is that the electromagnetic field is typically solved on a fixed grid in the background. So the EM forces are fixed. And then you have the two flavors. Either you have full pick, where both protons and electrons are actually individual particles, or to be honest, macroparticles, like a few million protons kept into one macroparticle. And for those particles, you compute the trajectory self-consistently using the Lorentz force. And if you use the Lorentz force and you couple that to the background electromagnetic field, you have the back reaction onto the field on that grid and can compute how the particle energy actually evolves. And then there's the hybrid method, where you say the cosmic ray or the electrons are too tricky because of the tiny gyro radii. You need insane resolution. So you say the electrons are also fluid, and I only care about the cosmic rays, the protons. And then you end up here with this hybrid model. So how does that look? Here are simulations by Guo et al. With electrons. Here you see the shock front. In color, you see one selected electron that moves in. Here is the gamma factor, so this is the energy, and color-coded is the time. So what you see is the electron comes in here. Here's the shock front, so it starts diffusing back and forth in the shock front, and via that process gets larger and larger elongation in the x direction, which represents the gyro radius. So that means more energy during this diffusion process. So this is pretty hard work, because this is one electron. And in the end, you would like to get a full distribution or full spectrum. So what you do here is statistical mechanics, brute force, with like billions of individual particles. So here's such a spectrum shown based on simulations by Damiano Caprioli. Initially, you put in this dashed Maxwellian distribution, so thermal distribution. You have a strong shock with a Mach number of 20, and then you let the protons, in this case they are protons, diffuse back and forth to the shock front. Color-coded is again the time. So blue is an early part. So here you see that you lift some particles from the thermal tail and put it into higher energies. And over time, you put more and more energy into a high energy tail. So that looks pretty flat, but I should mention here that what's plotted here is momentum to the fourth power times the particle distribution function. So in fact, this is all very steep, but just flattened to be visualized better. So with this kind of process, we see that cosmic ray acceleration, or acceleration from the thermal bath into the non-thermal high energy component, works. And it also works with the expected slope for a strong shock. I didn't show it, but that is in good agreement. This also shows how tricky it is to actually do proper cosmic rays. I showed you the spectrum with like 12 orders of magnitude, and with millions of CPU hours, they only got 1.5 orders of magnitude into the high energy. So it's really, really tricky to accelerate particles to very high energies. So let's look at astrophysical accelerators. So far, that was all theoretical shock fronts. Now let's look what we actually have there. So for the low energy cosmic rays, far below a GeV, you can have all kinds of shocks. The ISM is cold but fast, which means you have Mach numbers of 20 or so you get decent acceleration. Then there's stellar winds, they're pretty fast, dilute but very fast. You have accretion shocks or outflows from protostars and so on. So for very low energy cosmic rays, we're fine. If we would like to go into the relativistic regime, and relativistic here is above 10 to the 9 EV, and that should be 10 to the 15 EV, not GeV. So that's maybe a bit too much. So there, supernova remnants, as I mentioned earlier, are a good candidate simply for global energetic reasons. So here is an illustration of a supernova explosion. You have a strong shock front that runs outward. Then you have a reverse shock that goes into the center back and goes back and forth several times. And if we look at the energy that you put into a very concentrated small region, this resulting shock is coherent enough and strong enough to provide the conditions that we need for particle acceleration. Okay, so this is up to 10 to the 15 EV, but we've seen also much higher energies. And there we actually have a problem. We don't really know where these high energy particle comes from a first principle perspective. So instead, so we know supernovae are not powerful enough, and there's an exclusion principle in a sense, and we can exclude them based on the arguments of confinement. There's a so-called Hillas plot, but originally that was already mentioned by Fermi. And here, what you plot is the radius or the system size versus the typical magnetic field strength. So here's a supernova remnant. Supernova remnant has this size and observed magnetic fields of that strength. The lines here are the gyro radii for protons of 10 to the 20 EV. So this is something we would like to produce because we see it in the spectrum, but the gyro radius is much larger than the system size here. So if we wanted to produce these kind of particles in a supernova remnant, which means you have to confine them somehow to the diffusive acceleration, that means that for this size, you would need a much higher magnetic field in order to keep the particles to that small size for long enough such that you can do this diffusive acceleration. So with this exclusion principle, we can look at what kind of objects are in the range with size and corresponding magnetic fields that they can confine high energy cosmic rays. And then there are a few AGNs or gamma ray bursts with multiple shocks. And also neutron stars are some candidates because they have insanely high magnetic fields. So there we are a bit puzzled, but fortunately, these are the very high energies. And if we look at the dynamics of galaxies, we don't really care about those high energies. Okay, let me illustrate a bit. Once we have a couple cosmic rays, what happens to them? So imagine you have a magnetic field line and a cosmic ray that gyrates around that magnetic field line. If the gas is also partially ionized, then you keep the magnetic field line coupled to the atoms, which means if you move the cosmic rays, they move the magnetic field, and the magnetic field moves the atoms, so you have an advection with the gas. So this is only a very idealized picture. Now the magnetic field is not a straight line, but is perturbed. So instead of a simple gyration around the magnetic field line, you also have scattering effects back and forth of these magnetic irregularities. So if you were to derive a partial differential equation based on elastic scattering, you end up with a diffusion equation to first order. So from that simple arguments or picture, you can find out that cosmic rays can diffuse relative to the gas. And while there's still gyrate around the magnetic field line, it's sort of illustrative that the diffusion is mainly along the field lines and not perpendicular to the field line. That's only half the truth as well, because elastic scattering is a very simplified picture, because we have magnetic waves. So if you have a resonant interaction between a wave and a particle, then this scattering is not elastic anymore, but you will transfer energy. I mean, you can probably all picture how a gyro-resonant interaction could look like, but in order to picture it a bit easier, imagine you are cosmic ray and you ride your bike, and your gyro radius is approximately the size of your wheel. As long as the wiggles on the street are much smaller than the wheel, you're all fine. But as soon as the wiggles in the street are approximately the size of your bike, you will have resonant interactions and you will definitely lose energy. So this is exactly what happens here as well. And the cosmic ray and magnetic field interaction will therefore transfer energy, and it's not an energy conserving diffusion process, but so-called streaming. That's another awesome work from the 70s, pen and paper work, where people equate energy gains and losses, damping rates and growth rates, and therefore come up with this streaming instability. So it's quite complex, but what I would like to highlight is, if you have a cosmic ray population and you just advect it, it keeps the shape of the distribution. If you have a diffusive process and you start with a sharp peak, then it will diffuse and will get Gaussian wings. If you are in the streaming limit, then as soon as cosmic rays would like to go faster than the Alfvén speed in this case, they have this resonant interaction and will be slowed down efficiently. So as soon as they want to go faster, they hit the wall of resonant interactions. That's why in a streaming picture, you have very sharp edges where these edges move with the Alfvén speed. So now, this is the microphysics example. So let me jump to a point where we can actually use that in large-scale simulations and ask the question, are cosmic rays actually a fluid? So we see for thermal fluid, we have direct particle collision. That's the definition of a fluid. In case of cosmic rays, we have interactions with the B field. However, many gyration around the field line, such that if you integrate over a large volume, it's comparable. We have fast thermalization with the Maxwellian distribution. For the cosmic rays, we have seen that there are complicated distributions with a long non-thermal tail. And then we also have here an isotropic distribution function. And here, because of this anisotropic transport, is an anisotropic distribution. So there are a few fundamental differences, but we can still treat them as a fluid. So let's now put that into simulations of the interstellar medium. So here I have boxes with half a kiloparsec in size. That means several individual molecular clouds and supernova remnants fit in there. I have periodic boundary conditions in X and Y and very elongated in Z, such that I can see whether some sort of outflows appear. And then I put in supernovae with thermal and cosmic ray feedback. The thermal component is something like 10 to the 51 ergs, and the cosmic rays have an efficiency of 10% rule of thumb. So 10 to the 50 ergs in cosmic rays. So first, let's look at the simulation without cosmic rays. Here you see the time evolution of over 150 mega years, only with supernova explosions that are located here, and only thermal energy. So the supernovae explode, they are bursty explosions, they shape the structure of the interstellar medium, they push some gas out to a height of 2 kiloparsecs, but above the region where the cosmic rays explode, you lose the thermal support, the gas cools, and at some point, the material clumps up there and falls back. Similar to this part of cloud that gets pushed to 1 kiloparsec, there are no further supernovae at that height, and then the gas can clump and cool and fall down. Same here. So you get the classical counter flow effect. if you now include cosmic rays with 10% efficiency, structure looks completely different. You have the same supernovae at the same locations. They shape the structure where they directly explode. But then in addition to that, we get this relativistic fluid that cools less efficiently and can diffuse relative to the gas. So the cosmic rays are injected here with the supernovae, then diffuse to larger heights. They build some sort of a background soup with a pressure gradient that points out of the disk. And gravity points towards the disk. And if you do the math, then what the cosmic rays can actually provide is they can compensate for the gravitational forces and therefore allow to lift the gas. And what is very important in that process is that it's a slow lift of gas. You just make sure that you compensate for the gravitational attraction. It's a little bit like an elevator effect, where in every good elevator, you're not shot to the 20th floor, but the elevator makes sure that locally you compensate for gravitational forces and lifts you up. So I'm not the only one who has done that. There are various kinds of numerical setups with isolated galaxies, patterns of the ISM or cosmological simulations, and they all agree to first order that cosmic rays are very good candidates to drive outflows and shape the galaxy, but the details are complicated. Let me give you, maybe I'm a bit ahead of time, so maybe so I said the cosmic rays are a good candidate. The details matter. And here I would like to highlight 3 different branches of cosmic ray research that now push the limit. The one part is cosmic ray transport. This is one of the big construction sites. So we have diffusion and streaming, but as I said, there's a lot of pen and paper work, and we need to do more self-consistent models with the magnetic field, with the waves, and so on. The second part is we would like to have a full cosmic ray spectrum. For the dynamics, I mentioned that we are only interested in the GeV protons, but in order to do a proper comparison to observation, we also need to cover the full energy range and therefore have the detailed cooling and interaction processes. And then most of the energy is in protons, but in order to do a detailed comparison, we would like to also simulate boron. We would like to include electrons, secondaries, and unstable isotopes to actually match more with observational details. So one word about the coupling of cosmic rays with the gas and the magnetic field. I already showed that picture that in simple diffusion, you get Gaussian wings. With the streaming, you get top hat functions that shape, that move outward over time. So Timon Thomas has done an awesome work in combining all of that self-consistently and computed the combination of where diffusion dominates, where streaming dominates, and he finds this kind of distribution. So you clearly see in some ranges, you see the Gaussian wings. In other parts, you see a flat plateau where we're dominated by streaming. And then you can also compute what are the effective transport speeds that you get from this diffusion and streaming combination. And this is actually a bit of frustrating plot. This is, as a function of cosmic ray energy, the transport speed or the diffusion coefficient. And it varies by 10 orders of magnitude. So every simulator that has tried to put in 10 orders of different parameters will hit the limit of practicability. The second part is, what do we do in terms of full cosmic ray spectra? This is actually where I spend a lot of time on numerically and brain power wise. So I mentioned already that we are interested in the low energy parts for ionization, the pressure, and then the link to gamma ray observations, and doing a post-processing of existing cosmic ray galaxies, we can check how likely is it, or where do we expect steady state spectra, which are intrinsically assumed if I only take the GeV cosmic rays and assume a uniform spectrum, and where are details of the spectrum important. And Maria Wehrhahn found out that basically for half of the galaxy, you would expect different spectral shapes. So it's of interest to also deal with the details of the spectrum. So I put in a lot of effort to actually simulate that efficiently and have a full cosmic ray spectrum in every computational cell. And this is a simplified galaxy simulation where we show the full cosmic ray spectrum in every cell. So here I have a spectrum that ranges from 100 MeV up to here in total 100 TeV. And as we mentioned with the boron to carbon ratio, high energy cosmic rays move faster. So these are the low energy cosmic rays. They're injected where the supernovae occur, but then they don't get very far and cool. The GeV cosmic rays are faster, which means they're injected at the same locations, but can spread much more. And then the TeV part looks very smooth because the transport is even faster. Here are a couple spectra for the center of the galaxy, some outer disk where approximately the solar circle is, and then for some outflows. Here color-coded as a function of time, here at one point in time, color-coded with different heights. And I don't want to go into detail, but what you can see is those spectra are far from universal. Depending on where you are, the spectral shape differs, sometimes a bit less, sometimes a bit more, but the spectra are really fundamentally different in different corners of the galaxy. We can also quantify that a bit in the dynamics that we see in galaxies. So here, for instance, are spectral cosmic rays for a dwarf galaxy, an intermediate mass galaxy, and a Milky Way system. And if you ask, how is the bulk of the cosmic ray energy transported, then you would integrate over the spectrum and compute where's most of the energy going, with what speed. If you do this, then this is the effective transport speed or diffusion coefficient that you get purely because of shapes or variations in the shape of the spectrum. And this spans 2 orders of magnitude. So without spectral variations, that would all be one color. But with the spectral variations, the effective way how the bulk of the energy moves changes depending on the location of the disk and the model that we use. This is all very cosmic ray abstract numbers, but you can also look at the structure of the galaxy. So here is an example without any cosmic rays, and similar to the stratified boxes that I've shown before, there's not much outflow. The disk is thin, maybe a kiloparsec, but here the scales are larger. If you include cosmic rays only with the main pressure, then you get a thicker disk, some outflows. The temperature of the CGM, so circumgalactic medium, is lower, and we're closer to what we expect from the stratified box simulation. If you now include spectrally resolved cosmic rays, where individual energies are taken into account, then you see an even more dramatic change of the circumgalactic medium. You see a completely different structure of the temperature around the galaxy. And here's the ratio of cosmic ray to thermal pressure. I maybe don't go into detail here. So this is all the theorist's point of view. Let's now connect that to some observations. This is work done by Maria Wehrhahn, who has looked at gamma ray spectra and various models for the cosmic ray physics to see how they match. So this is the spectrum, and here we have in purple and green simplified cosmic ray simulations with only taking into account the total pressure. And then in blue, you see the model with the full spectral solver. And the data are fit better. Doesn't look too dramatic, right? I mean, it's just, 1.5 thumbs between the one and the other lines. But on the right-hand side here, you see how the galaxy looks in gamma rays at 1 GeV, 10 GeV, and 100 GeV. And I will now flip back and forth between the steady state model and the full spectral model. Here you see, with the spectral model, high energy cosmic rays can get faster further out, and the galaxy looks completely different compared to the model with only steady state. So if we want to do detailed comparison of gamma ray observations in galaxies, then we would need a full spectral model. Finally, I want to touch quickly on the third point that I made, which is that we need to go beyond the cosmic ray protons. So I already mentioned that we would like to do boron to carbon ratio and so on. But let's start with the simple ones, with electrons. So here Georg Winner has done an implementation of cosmic ray electrons where he follows also full spectrum and does a comparison between individual supernova remnants in observations and the corresponding simulation. And by doing so, you can actually try to match very carefully the observational parts in radio, X-rays, and gamma rays, and therefore deduce how the cosmic ray electron properties, transport and acceleration efficiency, and so on, can be constrained, and how when they match. So there's quite a bit of stuff in here. So for instance, how the acceleration efficiency depends on the angle of the magnetic field. That was completely differently predicted from particle and cell simulations compared to what you can see here in comparison to observations. And then furthermore, how strongly the field needs to be amplified behind the shock with like different amplification processes and so on. That's one individual supernova remnant, but here are also large simulations from galaxy clusters, which basically use a similar technique to constrain the parameters and connect to observations. Besides the electrons, here are also the models with different secondary particles. Here's again the boron to carbon ratio. And there are many species done already in a steady state approach. So no live hydrodynamics, but you say you have a static galaxy, you have constant injection, then you compute what is the steady state solution for different cosmic rays and how large the diffusion coefficients, the losses, and so on need to be in order to match the data with some simulations. There are very famous codes like Galprop. It has been around for more than 20 years. Dragon and Picard. This is a result shown from Ralph Kissmann. And that works okay for Milky Way galaxies. However, the Milky Way galaxy is also in a sense a bit boring. We don't have starbursts. We don't have major mergers. I mean, fortunately for us, but you know, from a galactic perspective, kind of boring. This approach has also been tried in MHD and full cosmological simulations with various species here and the resulting spectra and observables. But I can tell you there's a lot of details in the numerics that we have to solve because you have like 3 spatial dimensions, then you have the momentum plus various different species. So you end up with like 5, 6 dimensions in the simulation, and it's numerically quite tricky. Finally, I would like to show one example of how we can use this with electrons to actually check whether what we see is correct in terms of what we expect from models. So this is work by Joe Whittingham. He has done a very similar approach of the cosmic ray electrons. He has put them in a large-scale cosmological shock. Then, in different positions, he computes the details of the cosmic ray electron spectrum with various losses. So here are individual particles. Then you get various shapes and slopes of the cosmic ray spectrum. I don't want to go into detail, but what you can do is you can couple the cosmic ray energy density to the magnetic field via radio synchrotron emission. So the electrons gyrate around the magnetic field. The electrons lose energy by that process, and there this shines in radio. And then what he did is he looked at the magnetic field strength in his simulations, computed from the MHD equations, and he looked at the magnetic field strength that you would observe by doing radio synchrotron emission. And you can see that they differ. This is a very clean, simple shock on very large scales, but it would tell you that you would completely overestimate the magnetic field strength if you were to use a simple modeling or too simplified modeling for the radio synchrotron emission. So this is only done or this is a problem at the infancy state, so we need to go far away to do much more of that. But it illustrates how we can use these kind of techniques. And with that, I would like to come to my take-home points. So what you should take home is that cosmic rays mainly interact with the magnetic field. So there are no particle-particle collisions. If you talk about cosmic rays, you need to talk to the magnetic field in any case. Then what you should take home is that cosmic rays are attracted with the gas and diffuse and stream relative to the gas. So this is an energy density that is not confined to the gas motions. In the ISM, we find sort of equipartition, which means cosmic rays are really a decent energy reservoir. And via the coupling, they can drive warm and smooth outflows here. That is comparable to what we observe. And then there are the to-dos, or the construction sites for future cosmic ray applications. One is a new transport scheme from scratch. So doing particle in cell simulations with very many particles in various conditions to determine exactly how much energy is transferred to the magnetic field or taken from the magnetic field and so on. And then we need light spectra in many applications, in particular, if you would like to compare that observations, both for protons and then for all the secondaries in the next step. And with that, I would like to thank you.
Thank you very much, Philip. That's a very, very clear basic physics. In the end, there's still a bit of work to be done in terms of understanding the propagation. But I'm sure there will be some questions both from the online and in here. I'd like to start with questions from students, if they have any, please. Yep.
Hi, thank you for the talk. Thinking about the gas reservoir of the galaxies, when you compare the simulations with and without the cosmic rays, do you see a significant difference in the neutral gas fractions of these galaxies? Are you able to compute that? Or?
The neutral gas fraction?
Yeah.
Yes, so in the disk itself, where most of the mass sits, we don't see too dramatic differences. But what we see is that in the case of cosmic ray-driven outflows, the gas here above and below is much warmer, is much colder compared to the thermally driven 10 million gas from supernovae. So therefore, we find easily neutral or warmish outflows compared to the hot outflows. So there we really see a change in the neutral fraction, also at relatively large heights. So that was here, where the cold temperatures of 10 to the 5 Kelvin and therefore more neutral gas can extend to much larger heights, but not really in the disk. So the disk itself is not changed completely.
Okay, another question from a student, otherwise we'll move on. Okay, I'll open the questions to everybody. Any questions? Yep.
Why is gravity not entering? You have this equivalence of various energy forms and kinetic energy, and why is not at that place gravity entering?
So, well, in principle, we can also put that in, and we computed the ratio of gravitational energy to the others, and that's also comparable. So if you look at the acceleration profiles, then you see that gravity and the rest is very well balanced. So this is also a bit of a self-regulating process, because if gravity is a bit stronger, then you get more gas towards the galactic disk and more star formation that self-regulates. But what we see is that, including cosmic rays, we just push the limit a bit above gravity, and then we can lift the gas off. It's not like an explosive part, it's a little bit, but consistently over large ranges, so that's why you can actually lift the gas.
Right. If I could just ask a question, I mean, now you didn't use the word wind. I mean, you're actually releasing gas out of the galaxy, right? Into presumably the circumgalactic medium. And that's a big feedback effect, which presumably will hinder the accretion of gas onto disks. And I'd like, could you comment on how important that process is in regard to other feedback processes maybe going on in the disk on smaller scales?
So I didn't use the wind in a galactic perspective because very often we don't see terribly high velocities from the galaxy. So they slowly build up. And if you look at the classical wind that really escapes the halo and completely regulates the amount of gas in the halo, then I think we don't have a conclusive answer. So that falls into the category where the details matter. And then the question is, how good do we model the transport and the effective speeds of cosmic rays? Is there actually a feedback that is active feedback and kicks out the gas, or is there mainly preventative feedback that already fills enough volumes with cosmic ray pressure early on in the cosmological evolution such that less gas falls in the first place? So these are things that we need to look at with detailed ISM and also in the cosmological context. And therefore, the classical wind that kicks out everything is, I try to avoid that.
All right, that's interesting. I mean, you're very zurückhaltend there. Another question. I don't see anything at the moment. There's also nothing online. If you have a question online, please type into the message, into the chat. Could I ask another question? You had this intriguing comparison between the radio, the simulated, the synchrotron image with the shock. I think it was Whittingham. Oh, yes, this one. So, and you mentioned that the radio was more prominent than you had predicted. Are you predicting the magnetic field as well as the cosmic ray distribution in that? Because of course there's two variables for the radio. Yeah, I mean, you've got the
So for the magnetic field, we simulate the magnetic fields in the simulation.
You're right.
In that sense, we don't need to predict them.
Yes, I know, but I guess I'm talking about this. This is a shock. So are you producing magnetic fields in the shock? You know, through plasma instabilities in the shock. Did you have that physics in? I'm just intrigued because you mentioned that there's larger contrast here in the observations or than your predictions. So I'm interested from that perspective.
So I think what we have in there for sure is magnetic field amplification via small scale dynamo and compression. If you look at more physics in terms of magnetic field details, subgrid turbulence, and so on, amplification, we don't have that.
All right.
But this is also something we don't require or include when we do these synthetic observations in order to do the comparison. Yeah. So if this is wrong, it's wrong consistently.
Yeah. I guess I'm a bit confused about the real. These are pure synthetic data you've got here. But I mean, if you do a power spectrum analysis, compare it with real data, is that something you could that could feed into this?
That is work that is currently ongoing, and also to quantify a bit what kind of correction factors you need to apply in order to match with the synthetic observations with the stuff that we actually measure. So in details of the spectrum, there's a lot of data there, but the community needs to apply that to various conditions, stronger and weaker shocks, different velocities, different environments in order to make a conclusive statement.
Okay. Then I think we slowly wrap up. I'm looking again online. I don't see any questions. If there's no other questions here, then I think we'll just slowly wrap up. Before we thank Philip, I'd like to announce next week's colloquium. And we're sort of moving on a little bit onto somewhat larger scales, where Aurora Simoniescu is visiting, and she has got some fresh off the press data to show us. She from X-ray spectroscopy on these feedback systems in clusters of galaxies. So we'll look forward to that. In the meantime, let's thank Philipp again for this extremely informative and interesting overview of this really interesting work. Thank you very much, Philipp.